Okay, well, my name's Euan Mason. I think many of you may know me. I'm a professor at the School of Forestry. My specialty is in growth and yield modeling and silviculture, and become a bit of a physiologist as well. And I make models that combine physiology and stats and growth and yield modeling principles. This is my colleague, Dr. Justin Morgenroth, and you want to say what you are and
Sure.
where you're from and that sort of thing?
So the side of things that I address here is site description. So Euan's growth models rely on describing the site, and that's where I try to contribute.
Okay. And Sirajis, do you want to say something about yourself?
Thank you. Hi, I'm Siraj Salikin from Bangladesh, long way away from here. What I'm trying to do, I'm combined Professor Euan Mason's and Dr. Jackson Morgenroth's interest in a same ground to make it accessible to the tree breeder or in forestry. Yeah, so
Okay.
check.
G'day, I'm Jake Burgess and I'm a local student that went to School of Forestry, did my undergrad there and continuing to do my Masters under Euan and Justin supervision. And my focus really is on the demonstration trials that Shaf did mention earlier in his talk and sort of trying to model their growth and how they are represented around the country.
Okay, thanks, guys. I'd like you to stay up here if you like, because they may ask you some funny questions, and you guys know the answers. So, is that all right? That's good.
That's the
Okay.
nice part about Euan and I. These guys do the work, and Euan and I get to take all the credit for it. So it's a good setup.
Yeah. So what we're talking about with this particular topic is we want to try and answer the questions that potential investors will ask when they consider growing these eucalypts. So they'll want to know things like, where should we put different species? What kinds of sites will they do well on? And they'll want to know, how should we tend them? How many trees should we plant? What are the likely rotation lengths? What is the potential for coppice? Questions like that. How are we going to regenerate them? What kind of growth and yield can we expect, and when? And not only that, what kinds of products should we expect? So we need to focus, of course, on heartwood yields, not just on total stem volume yields. They want to know, and of course, we have some funding. We need to acknowledge our funders. The AgMart grant has been very helpful for us. We've got an SWP project, which I believe comes from the NPI. That's your focus, right? And the Forest Growers Levy Trust also, funders. So, firstly, what kind of delivery might you expect for the kind of knowledge that we hope to generate and that we are generating? Well, this is part of a decision support system that's available online, and it's aimed at matching species with sites, with enabling people to tell the system what their objectives are, describe their sites, and then the system will come up with lists of potential species and some information about how those species may perform on those sites. So you can call up Google Maps, and there's a layer we put behind Google Maps, and you click on where your site is, and a whole lot of information that you can see on the right there spills out about your site. And that's then brought into a system where you can click go, and it gives you lists of species that might perform well, and it shows you something about their productivity and some of the limitations. It shows you something about the various estimates we can get from the information that users have provided. And that'll be one of the mechanisms that we use. Which brings us to Siraj's PhD project, and you will begin talking about now. So.
Yeah, sure. So one of the key things of this whole project is that the different species that we've got planted throughout Marlborough, Canterbury, and the east coast of the North Island are responding differently to the sites. You'll see a picture in due progress, but what you'll notice really is that within a single site, something that's only a couple of hectares, you've got massive differences in growth. And what we're trying to do is understand what site characteristics are influencing the good growth, the bad growth, as well as the mortality. And so that's a lot of what Sirajis is working on as part of his PhD project. He's looking at microsite as well as between site variation in growth and environmental conditions. He'll be producing a complete growth and yield model for Eucalyptus globoidea, and he'll be producing an initial yield model for Basistowana. All of this will be delivered in the DSS framework that Euan briefly introduced. So he's got 4 trial sites. 3 of them are here in this region, and 1 on the east coast of the North Island. So this probably gives a bit of an impression for the type of I guess, within site growth that you can see at some of our trials. So here's, I actually don't know what site this is.
This is Larson.
Lawson, okay. So,
Lawson, yeah.
Lawson. So this is one of the aspects, and
This is the northern face at Lawson.
yeah, and
This is the east face.
here's the east face. So same time period, massive growth on one aspect, and relatively poor growth on another aspect. So here's another one of our sites. This is actually a photo taken by Sirajas. It shows really, well, it shows exactly the problem that we're trying to address. Some sites have, wonderful growth in one area and really poor establishment, even mortality in other areas altogether. So what we're trying to do is really understand why a tree on this particular square patch or square meter patch of soil grew really well, and a tree over here on another square meter of soil grew really, really poorly. And so that's the driving sort of question behind Sirajas's research. To answer those questions, we are trying to describe in as much detail as possible the soil, the climate, and the topography within a given site. So Sirajas has achieved this by digging numerous soil pits at his 4 trial sites with the help of the local landowners. Trying to do it by shovel proved to be a bit too difficult. So he's been digging these meter-deep soil pits, characterizing soil texture, bulk density, soil moisture retention, soil chemistry within the different horizons. We've also deployed a number of soil moisture sensors throughout these different sites that are logging volumetric soil moisture data at 30-minute intervals. And again, we were trying to scatter these throughout the sites as much as possible to obtain as much description of within-site variation as possible. In terms of climate, climate surfaces are available from NIWA, for example, but those in some regards differ quite a bit to a very local scenario. So unless you happen to have one of NIWA's stations in your backyard, then we need to sort of establish these climate stations. So these climate stations are measuring wind, precipitation, radiation. There are air temperature sensors scattered throughout the sites as well, and these data are captured at 30-minute intervals. And so that just gives you a rough idea for where, within a site where you have the sensors scattered. Again, we're trying to describe the variation within a site so we can know with certainty why up here you've got great tree growth and over here you've got poor tree growth, that type of thing. And then the final thing that we are describing within and between sites is the topography. So the key surface here is the digital elevation model. And some trials are established, fortunately, within areas for which there's LiDAR coverage, but most trials are not. And so what we're doing is we're using a survey grade, or I guess a mapping grade GPS unit to do a poor man's version of LiDAR. So we're getting accurate XYZ coordinates every couple of meters across an entire site. So there are thousands of individual elevation points that describe a site, and then producing these digital elevation models. Once you have a digital elevation model, you can produce a number of other surfaces, things like a slope surface, an aspect surface, curvature, wetness, cumulative radiation, roughness, and all of these different surfaces can be used to describe why we're seeing differences in growth within a site. So, with that side of things taken care of, once you've described the site and you know the tree growth at a site, you can start producing these pretty pictures. So over to
Okay,
Euan.
sure, thanks. Yeah, so this is a really interesting program, especially for somebody who's used to working with radiata pine and who's had the benefit of literally thousands of permanent sample plots that cover entire rotations on a huge range of sites. With these species, we're dealing with just a few PSPs, and we now have several hundred PSPs, but they're all very young. We don't have a lot of data about growth of old crops, and that's going to limit what we can deliver. So our task is to make the very best we can of a limited set of information to try and provide guidance to growers until such time as we have these measurements in older stands. So what I'm going to show you here are mostly plots of very young growth, first 5 or 6 years, and to show you just some of the things the patterns that we can already see emerging in the data sets. For instance, this is on one particular site down the road at Avery's farm, where that was the site that you just saw that has that peculiar shape. It's a very, very dry hillside. It has a disparaging name. What's the name they call it? It's like the death of, so what's that?
Poverty Knoll.
Poverty Hill, yeah, Poverty Hill. And so this is a really dry site, and the sorts of rainfall that we're getting there in some years is less than 300 millimeters a year in some years. And the soils are not terribly good. But what you can see, for instance, is that when you take just one variable, like distance from the nearest ridge, that the further you are from the ridge, the further the trees are from the ridge, the better they're growing. So there's 125 meters from the ridge is more red, and 25 meters is pale yellow there. And pale yellow tends to be down the lower end of the graph, and the red is the top of the graph. Similarly, and these two are correlated, these measures. Another way of expressing that is by local curvature. Now, what we mean by that, it's sometimes known as topographic index. You take a particular point in the landscape and you look out to neighboring points, and you look at the differences in elevation. You take the cumulative difference in elevation, those between your central point and the points around it. And so for a site that has convex curvature, where the site may be on a ridge or near a ridge, on a little knoll, you're going to get a negative number. And for a site that's in a little valley, you're going to get a very positive number. And again, you can see these patterns emerging with the sites that are on the knolls tend to be doing more poorly than those within the small, very local small hollows. For one species, we have some older data. But again, with this species, we're not dealing with thousands of PSPs. We're dealing with just a couple of dozen PSPs. Permanent sample plots. So for those who are not in forestry, permanent sample plots are a really important part of growth and yield modeling in forestry. We successively measure growth within these plots at different times over the years, and then we build patterns of looking at what the nature of the growth trends are, and we build these families of equations that describe the trends. And you can see that we don't have many plots here. But we've done the best we can in fitting a model to the height growth across the years. And then in any particular site, if you can know where you start, supposing if you know you start there, then you expect the trend to continue along that curve. It's really quite simple. Now, these species are strongly influenced by local weather conditions, by changes in weather from year to year. So this kind of model is really likely to be inadequate. And so the next step is to build into these models some physiology. And so those are called hybrid growth and yield, ecophysiological and growth and yield models. So we are aiming to build hybrid ecophysiological and mensurational models for these species to take account of those variations in time and in climate conditions. Jack Burgess is working with the species that Sir Rogers is not working with, so there's not too much overlap between their studies. And Sir Rogers is looking at both microsite variation and macrosite variation. Jack is looking at just macrosite variation, but with a larger number of species. And his objectives are to derive models of mortality on those sites, to give initial yield models, given that we're dealing with very young data sets for these species. So we won't be able to tell you what happens at the end of the rotation. We'll have to wait and see in future years. But what we can do is say, well, this is what we have so far. And then he'll deliver a decision support system implementation of that knowledge. So we have data from 28 sites. He's looking at height and diameter at breast height. We're looking at a range of site characterizations, so LiDAR and GPS-derived digital elevation models. We want those models, those digital elevation models, to be as high resolution as possible. We have on-site climate stations, and/or there's a system, nationwide system called the Virtual Climate Station Network that the Met Service has. So every 5 kilometers across the landscape in New Zealand, there is a point, and at that point, weather is estimated from by interpolating between Met stations and taking account of local topography and so on every day. And that's been happening since 1962. So one of our first tasks was to find out, well, how good are these VCN estimates, VCSN estimates? And in fact, what we found is that for many of the variables that we're interested in, they're pretty good. Unfortunately, for rainfall, they're not terribly good. And so we need as much as possible to have local estimates of rainfall in our sites. And we're looking at on-site soil data collection and also using a new mapping system called SMAP for our soils. These are mean height trajectories by species, and a couple of interesting things here. Most of those involved with this project know that quadrangulata seems to grow quite rapidly on many sites, and that's reflected here. So these are quadrangulata sites. But look at this. This is really interesting. That's something that we've just become aware of recently, that this is quadrangulata growing in Hawke's Bay. And we're seeing a sudden decline in growth, and we don't know why that is. It could be variegated beetle. It could be a change in the climate in those years. But something has happened to make the growth of that species start to slow down prematurely. And so that's an interesting finding. But you can see that there's a huge range of productivity across just the species, even if we don't take account of the sites. If we look at a couple of the species by location, you can see the location really makes a difference as well. And so our task is to understand what the driving variables are that cause these differences between sites for these species, and differences in performance across sites. So here's Cladocalix across sites. Somebody had a question? Heard a mumble down the front here. As a university professor, you become really, really sensitive to mumbles. Usually at the back, though. They're not usually down the front.
It used to be up the bay.
Yeah, yeah. Oh, there you go. Yeah. So further work, because we have limited data sets, we're going to use people's experience as well as data. So there's a process that's called knowledge elicitation, which involves a series of interviews. And we're going to be interviewing people to try and gain what we can from and put in a coherent framework the knowledge that they think they have, then we'll try and implement that within the DSS. The decision support system that you saw combines both people's local knowledge and also data and knowledge derived from data, and it combines them into a coherent framework. So we're looking to do that for these species. We need to do some biomass and some leaf area index assessments. That's an urgent priority, and we're discussing how to implement that right away. If we're going to make any sense from a process point of view, from an ecophysiological point of view of the information that we have, we really need to do that. The taper and volume equations there are 1 or 2 online for some of these species, but they don't take account of heartwood, and you can see on the right-hand side the kind of thing we envisage, that we'll have taper and volume equations. So the taper and volume equation for the uninitiated is an equation which takes the diameter at breast height, which in New Zealand is at 1.4 meters above the ground, and the height of the tree, of an individual tree, and it describes the shape of the stem, or predicts the likely shape of the stem. And once you know that, of course, then you can start to cut that stem up into logs and begin to develop an understanding of the kinds of log grades that you can collect from that individual tree. And it's the foundation of mensuration to have that really good understanding of volume of individual trees. Well, we need also volume of heartwood, because heartwood is where the money is for many of these species. So that's what you can see on the right-hand side. It looks a lot better on my screen actually than that one, but This bit here is what we envisage, perhaps a heartwood taper equation. It's completely fictional. None of this it's not made from real data, but this is the kind of thing that we envisage building once we have the numbers, once we have the data to generate that kind of model. We need to know impacts of tending and genotype and build this in with Tara and her students' works to understand the effects of pathogens on growth and yield. So we're looking at developing some spacing experiments. There's one particular one that's called a Nelder design, which is an interesting way of doing that. We want to incorporate genotype in these models, and of course the influences of pathogens on leaf area index, particularly, and photosynthesis, and perhaps on the development of heartwood. We see those as priorities. A lot of that, as I say, it's further work. It may not happen in the next 2 years, but it's certainly the kind of information that growers need in order to make these decisions. So in summary, we want to provide the kind of information that a grower will need in order to make a reasonable assessment of what species they should use, if they want to grow these species, on what kinds of sites, and what kind of return they might get on their investment, and also what kind of risk they're likely to encounter when they grow these species. Those are really important elements. We want to help those growers with a site selection via an online decision support system. It already exists for other species. We want to build these species into that system. We want to incorporate also growth and yield models that are site sensitive, that include heartwood in their outturn, in their predictions. And we currently have 2 very able postgraduate students working in this area, and we anticipate more in the future. So that's it, right?